This conference will now be recorded.
So welcome everyone to another OCP Tap session. This is the 68th, basically, series. So again, we have here Dana Weinstein, which is going to give us a presentation about integrated acoustic resonators in commercial FinFET technology. Thanks to Hisham for making the intro. We'll do as usual, like with the like the bio for the speaker. So Dana Weinstein is a professor in Purdue Elmore Family School of Electrical and Computer Engineering and Associate Dean of Graduate Education in College of Engineering. Prior to joining Purdue in 2015, Dr. Weinstein joined the Department of Electrical Engineering and Computer Science at MIT as an assistant professor and served as an associate professor there between 2013 and 2015. She received her BA in physics and astrophysics from University of California, Berkeley in 2004, and a PhD in applied physics in 2009 from Cornell. Working on multi-gigahertz MEMS. She's a Purdue faculty scholar and recipient of the NSF Career Award, the DARPA Young Faculty Award, the first Intel Early Career Award, the first TRF Transducer Early Career Award, and the IEEE IEDM Roger A. Hacken Best Paper Award. Dr. Weinstein current research focuses on the innovative micro-electromechanical devices for applications ranging from MEMS IC wireless communication and clocking to micro-robotics, acoustics, and ultrasonic simulation. So today's talk is, as I said, about something very interesting with FinFET. And with no further ado, Dana, the floor is yours.
Thank you so much, Ahmed, and thanks to everyone. I'm excited to be invited to give this talk and to hopefully get a chance to hear from some of you as well about applications of our devices, of our technology. So again, my name is Dana Weinstein, and over the past 15 years plus, starting to get a little long there, we've been working on MEMS resonators, specifically scaling to high frequency, with a focus on integrated circuit implementation. So we're really interested in kind of lowering the barrier for MEMS devices, micro-electromechanical devices, to enter integrated circuits and to be kind of commonplace among circuit designers to just plop them into their layout. That's of course particularly prevalent now with our supply chain issues with integrated circuits, but also thinking about next generation wireless communication, timing and clocking opportunities, and a lot in that space. So leveraging a lot of the semiconductor industry boom that we are all anticipating with the CHIPS and Science Act. There are opportunities to embed MEMS devices and MEMS functionality into integrated circuits. Ahmed mentioned that we are working, beyond that, in devices like ultrasonic transducers and gallium nitride power devices, and leveraging those with MEMS capabilities. But I want to focus today on silicon-based integrated circuits and really lowering that barrier for IC integration. So the primary motivation, at least over the past decade plus, that we have looked at integrated circuit-based MEMS resonators has been in frequency sources and in filters. So part of that push to scaling to high frequency acoustic resonators, basically resonant tanks that could be integrated in ICs, include automotive applications and sensors, but 5G and 6G communications as well, terahertz and millimeter wave imaging, spectroscopy at terahertz frequencies, smart infrastructure and being able to embed sensors with radios, ideally with in-sensor computing, all built into monolithic chips. But then you can do fun things like oscillatory logic, non-Boolean signal processing, and things like that. And of course, as you scale to high frequency, KT equals H bar omega, you can get closer to ground state without a dilution fridge and start to think about things like quantum computing. So why MEMS devices? Why these micro-electromechanical systems at these frequencies for these applications? Well, there are several benefits, particularly over LC tanks that can be manufactured on chip, or even quartz crystal references, which are off chip but at much lower frequencies. One benefit, of course, over LC tanks is the high quality factor of acoustic or vibratory resonators. We can get typically frequency quality factor products of about 10 to the 12, 10 to the 15, depending on the substrates and the materials where the vibrational mode's existing. And that translates directly to low noise oscillators, of course. They also have much smaller footprint than their LC inductor capacitor counterparts, their quartz counterparts, dielectric resonators, due to the low velocity of sound waves relative to electromagnetic waves. And of course, they take advantage of wafer level fabrication and packaging, which helps us with SWaP-C, right? Size, weight, power, and cost, but also can translate directly to performance in whatever implementation you're using. So what's missing with current transducers? Why haven't people been able to really achieve the integrated microscale hardware at RF and millimeter wave frequencies to date? There are some key challenges, and again, when I'm talking about scaling in frequencies, we're typically talking about the 1 gigahertz to 100 gigahertz bands or range, which encompasses, of course, existing hardware, with FM radios, GPS, Wi-Fi, and as some of you may know, you have many bulk acoustic resonators that are comprising your radio in your cell phone today to address each of the bands that are needed. And they're no longer quartz. They're at kilohertz and megahertz frequencies. These are now thin film piezoelectric devices, but they do require special process, special packaging, and different chips for each frequency band. And so you have many of them littering your circuit board today. The idea is to go monolithic and integrate it all. And then, of course, there are lots of new opportunities where hardware is still being developed to scale up to greater than 6 gigahertz frequencies. Some of the major challenges, and I won't go too much into detail on the technical side. Please feel free to ask questions at any time. But keeping it fairly high level, some of the big challenges are on materials and functionality. So the first major issue is on making sure that even at these high frequencies, we have efficient transduction or conversion of energy between the electrical signal, for example, what's coming in from the antenna, or from whatever previous stage of your circuit, for example, in a clock, to the mechanical vibration, and then from the mechanical vibration back into an electrical signal that can be useful somewhere else down the line. And so the electromechanical coupling, we call it K-squared, is very important for that. And it requires materials and it requires particular vibrational modes. It requires several considerations as you try to scale up. What it would translate to if we had much higher electromechanical coupling, or K-squared, in filters, that translates to low insertion loss or high bandwidth operation. You can make wider passband filters for instantaneous bandwidth. It also translates to, in clocks, of course, low phase noise and lower power consumption at the system level. And in sensors, it translates directly to signal to noise, so the SNR in sensor devices. Another big kind of holy grail topic is in tuning and in programmability. So I have these resonant tanks. I want to be able to tune them, whether it's for ad hoc radio. I'd want, ideally octave tuning. Okay, I will say that right now, that's not going to happen with MEMS devices that are geometrically defining frequency, which for clocks means you have a very stable frequency source. But you want to achieve some sort of tuning and programmability, on-off switching, being able to adapt to whatever the system needs. And so those are also things that need to be considered at the device level and in the way that we drive and sense acoustic waves in these structures. So I mentioned octave tuning, but transducer switching, linearity, and built-in capability to do computation with programmability can be a very nice feature, and people are looking a lot at in-memory computing, in sensor computing, which can leverage certain nonlinearities, hysteresis, and various other aspects which might be built into these devices moving forward. And then finally, another big important factor in defining these devices is the operating conditions. So frequency range, of course, is number one. We want to scale up in frequency. I mentioned why in filters, of course. In oscillators, you may be operating at lower frequency, but if your fundamental mode of your crystal, or in this case your acoustic resonator, that resonant tank, is higher, it means you don't have to multiply up in frequency. You have opportunity, as long as the quality factor is high, for low phase noise from the start fundamentally. And it may translate to lower power consumption and not having to multiply up as well. And so as long as you have an efficient resonant element, that higher frequency can translate to multiple benefits. But it means we have to engineer thinner films and maintain low loss at high frequencies. Environmental factors are also a really big component, of course. Stability across temperature, pressure, G-forces, radiation, and whether or not you're operating in aqueous or chemical environments that may be relevant to your device and to your system. So in terms of kind of state of the art of where acoustic resonators are today, the kind that are thinking and with opportunities to scale to these frequencies, I give a couple of examples. I don't mean to exclude any particular technology, but in terms of those that are most amenable to translation to product, we have a couple here on the left, and they are, and this one is product, in fact. So there are some different ways to excite these acoustic vibrations, to confine them, and then to integrate them with your circuits. An excellent example is the dual Bragg bulk acoustic wave, or BAW resonator, that's now commercial product at Texas Instruments. So this is a thin piezoelectric film, aluminum nitride, actually scandium doped aluminum nitride, very likely at this stage to get higher coupling, or K-squared. And it's sandwiched between these acoustic Bragg reflectors that basically form the acoustic equivalent of an optical mirror, right? So it's these Bragg reflectors are used in optics a lot to confine the acoustic wave, and so you have large vibrations in this beige region here. Hopefully, you guys can see my mouse, and then these reflectors of high and low acoustic impedance materials mean that the wave does not leak up or down into the substrate. And in this case, you can put your circuits down here and integrate monolithically. It also means, that because this structure is not released, it's not a freely suspended membrane, it is also more robust and addresses some of those challenges that I mentioned in operating environment, harsh environment operations. But just like the filters in your phone now that are most likely the released ones from Broadcom, the FBAR or film bulk acoustic resonators that have an air cavity underneath here and above. The thickness of the film defines the frequency. And so if I want multiple frequencies, I need multiple thicknesses. I'm going to need different chips for each one of those things. So that's one challenge. And it's done, kind of either separately from CMOS or post-processing on a CMOS chip. So in that case, there are thermal limitations associated with the thermal budget for the deposition of these materials. On the other hand, another popular approach is to use lithium niobate, which is a non-linear but highly piezoelectric crystal that is used a lot in optoelectronics, actually, but has some really nice electromechanical properties too. And these devices are typically freely suspended, so you can see this is a top view. And some interdigitated fingers to excite a field inside the lithium niobate, which causes it to squeeze, expand, contract, which launches these acoustic waves. And it's this freely suspended little bar that, based on its dimensions, in this case, lateral dimensions, so I can define multiple frequencies on the same chip, I can get a particular high quality factor and high efficiency modes excited. At this point, these are not, AlScan and lithium niobate are not CMOS integrable yet. Niobate not at all, but scandium, I guess people are exploring it as an option. Aluminum nitride certainly is and has been integrated on CMOS, and it does require specialized fabrication and so forth. Our approach, and one that allows us to scale to even higher frequencies and leverage existing integrated circuit technology, is to bypass all of these special materials and special processes and basically hack the CMOS stack to trick it into vibrating. And specifically, we're interested in vibrating the transistor layer of the CMOS stack. Here's a little cartoon of a FinFET cross-section, FinFET CMOS cross-section. So you can see the fins here along this direction. These are arrays of gates along the transverse direction. And you can see that the metal layers are patterned in a particular way that we can use in order and engineer in order to confine acoustic waves. So if we basically use what's there in CMOS, we can get no post-processing, no release step, CMOS integrated MEMS devices. We are, limited in frequency by the transistor cutoff frequency, which is, very, well above 100 gigahertz, depending on which technology you're talking about, but substantially higher than that for any advanced technology node, and by the lithography limit of the process, which of course, it's 14 nanometers in this case. Now people are talking about 2-3 nanometers. Of course, the feature size is still higher than that, but that gets us easily into 40-50 gigahertz frequencies of vibrations. So plenty of room to scale up there. And then we can leverage front end of line active devices along with the back end of line in order to excite and confine acoustic waves and manipulate them. So that's the whole idea. Now the question is, how do I use standard CMOS in order to drive and to sense acoustic vibrations? That is not what it was intended to do, but we can really leverage fundamental physics and use the forces that are generated from capacitors, from depletion capacitance in PN diodes, and various other elements that are inherent to the CMOS process. So there are a few CMOS-friendly transducers that we can take advantage of. Of course, there are no air gaps currently in CMOS. I still put that in here just because that is like the fundamental way in which these MEMS devices are typically driven and sensed. You have capacitor plates, parallel plate capacitor. I apply a voltage across these plates. I get equal and opposite charges. there's a force, an electrostatic force that attracts these charges together. Typically, my capacitor is fixed and held apart, but it generates a strain, right? Or it'll close the gap some amount. You can certainly pull in accelerometers and gyroscopes that are in your phone today as well, but typically it's designed not to do that unless you're making switches or relays. So that's kind of the fundamental idea. On the sensing side, I have a voltage across capacitors. If those capacitors are moving, right, that changes the capacitance for a fixed voltage, right? Q is equal to CV. And so I get a current when I get a change in the capacitance. And so I can read out that current and figure out what motion, what change in C in the capacitance, whether it's a change in gap or a change in cross-sectional area. There are ways to get that mechanical signal out through an electrical signal. So we can do the same in CMOS using the dielectric capacitors that are built in. So now I don't have an air gap, but I'm squeezing the dielectric. And imagine in the case of the FinFETs, I'm squeezing the gate dielectric between the gate and the MOS channel. If I bias the MOS channel, for example, in accumulation, I can get essentially a capacitor-like behavior, a linear capacitor-like behavior, and I can drive and sense acoustic waves that way. I mentioned PN diodes, same capacitance concept. Now it's a depletion capacitance that makes that change and experiences that equal and opposite charges now across the depletion capacitor. I could drive thermally. I could heat up my transistors locally or resistors. It's not terribly efficient, and it's not something that we've implemented, but that is a possibility and something that can also be used in order to tune mechanical modes as well. Piezoresistive sensing is possible. So if I establish vibrations, perhaps through capacitors or diodes, then I can sense the vibrations due to the fact that I'm dynamically straining the silicon in the transistors or in any resistor that I lay down. And I can look at the changing current across that resistor and translate it to a dynamic stress in my structure. And I can take that one step beyond, and I can actually use transistors in order to sense vibrations. And this turns out to be the most efficient transduction, particularly at higher frequencies. So in this case, I'm using strain, I'm using the piezoresistance in the channel of the transistor. And as I stress the material, I'm modulating the mobility of the carriers that are flying across it. But I'm also changing the capacitor, the gate capacitor. And so I'm field modulating the carrier concentration in the transistor, and I can pick up basically an amplified signal before all of the parasitics come in and kill us. So we've demonstrated a range of these devices in standard CMOS technology. Here's one example from my ex-student Bishoy Bar, who's now at Kilby Labs, Texas Instruments, using basically arrays of metallization above in order to define a particular acoustic mode that can only propagate at the transistor layer, basically creating slow wave structures. We are able to excite acoustic waves using the transistor layer MOS capacitors, and sense. In the middle, you see we have an array of these transistors, and in the middle of this resonance cavity, we have these sensing transistors to sense the vibrations. And we got Qs over 13,000 at 3 gigahertz using this mechanism. Of course, you can see that the signal is very, very low in this particular case. We also demonstrated in more advanced technology nodes being able to access higher frequencies using FinFET technology. And you see the fins here and metal layers above to prevent, again, define these resonance modes that only propagate at the transistor layer. We were able to demonstrate up to 32 gigahertz frequency acoustic resonance with quality factors over 1,000. So FQ products of almost 4 times 10 to the 13. So this concept works, right? Just a quick highlight of how we go about designing these things. So here's an example of that same FinFET technology. This is these works were published recently in Nature Electronics and in Frontiers of Mechanical Engineering. More in-depth details on FinFET, but also on prospects moving forward, which I'll talk about shortly. But you can see the resonator here. This is a top view of the CMOS stack. So you're seeing mostly CMP fill, just kind of dummy layers in all the metallization. But these are 100 by 100 by 80 micron probe pads for us to individually measure each device. And then down under here, under these metal layers, is actually the resonant cavity. So it measures something like 200 nanometers by a few microns in dimensions, with vibrations traveling in the plane of the wafer, and the frequency defined by the pitch. So there are ways, how do we go about confining the acoustic vibrations? I'll go very quickly through this to keep an eye on time. But again, borrowing from the world of photonics, phononics is a close parallel to that. We basically have to engineer the dispersion properties, the kind of relationship between energy and momentum in this metamaterial, in order to define slow wave modes that they're too slow to propagate into the bulk, too slow to propagate up to the metal layers above to the back end of line and be scattered or lost out of the chip, perhaps into the plastic packaging around it. And so we really want to confine them to where all that activity is happening in terms of the transduction, driving, and sensing. And so kind of leveraging the periodic structures and the kind of dispersion engineering that's been developed for optical waveguides, for surface acoustic waveguides, we see how that translates to CMOS, where we have no control over the thickness of the layers, we have no control over the materials in the layers, but we can define lithographically patterns in plane. So that was using those restrictions and those constraints, because we can't break the design rules for the foundry. They won't tape out our chip if we do that. So working within those constraints, we figure out what resonance modes can exist. How do we get them at the business end with our MOS capacitors and transistors, and define these slow wave structures. All right, those dispersion relations look kind of like this. I won't go into the details of what this is, but what I can say, it's kind of a hot mess, right? So you've got all of these different modes coming from the different layers, from the different I guess modes of propagation, shearing, expansion, and all of that. And you have to figure out in what frequency ranges does each technology allow you to confine acoustic waves. It's not completely arbitrary, and so depending on spacing and materials and so forth. It's also really important, and I cannot stress this enough, to do these simulations in full 3D. So it's a very, very complicated structure to simulate this entire geometry. It's a very complex geometry with multiple layers. Each one can contribute something different to the modes. And so we take these unit cells and we build up basically these blocks that say, okay, in this particular set of layers, we'll be able to have this kind of propagation, or we'll block this kind of propagation. Therefore, I'm going to space things in a particular way to match up with that. So 3D simulation is really important. But if anybody out there is working on more efficient finite element analysis, or FDTD, or and being able to do that with complex 3D geometries, please let me know, because that is one of our major limitations in being able to achieve the optimum performance resonators in round 1 of tape out. And in 14 nanometers, that tape out is expensive and slow, as some of you may know. And so it's really important for us to get as accurate a model as early on as possible. Ideally, we'd love to be able to simulate the full 3D structure and be able to capture spurious mode, transverse modes that come from the fact that I have a finite geometry, that there's an endpoint to this periodic structure that I've created. Because right now, with these kinds of simulations, you're assuming it goes off to infinity. So there are extra fun spurious modes that show up that you didn't intend. But the idea is that, I go and figure out which of these modes are viable for confining acoustic waves, which ones excite stresses at the transistor layer, and then identify those modes and define these, these phononic crystals around them to match up. All right, so that is what we did. Now that generates waves that can propagate in plane. Now I need to confine them so they don't go off, sideways to the rest of my chip, and 1, be lost, and 2, dynamically strain some amplifier down the line that will now have some spurious peak in it. So how do I confine those? Well, again, borrowing from phononic world, we can make adiabatic transitions that basically shift the modes so that they can't propagate in this region over here, because the spacing of the phononic crystal is different than here. So we do that sort of thing. An example of from our recent Nature Electronics paper, where we did a thorough characterization of the FinFET devices, not vibrating in the fin mode, that 30 gigahertz mode, but vibrating along the length of the fin. And if any of you are familiar with FinFET technology, you might know that there are these raised source and drain epitaxial silicon and silicon germanium regions that are kind of like these dumbbells. And so the spacing of those dumbbells will define the frequency. And you can see by changing the gate length of the transistor, we can change the frequency. You can also see some of these spurious modes that I was talking about due to the fact that that we have transverse modes that are not simulated at this point because of the computational energy that's needed to get that done, and being unable to capture the full geometry. Those can be designed out, certainly, which translates to higher quality factors, as well as higher amplitudes of the vibrations. And so those are things to come. Okay, but even so, we're talking about microsiemens of electromechanical transconductance. And what does that mean? Well, we've developed a full nonlinear, complex, Verilog A model that circuit designers can plug and play into their circuits to build oscillators or whatever component, whatever system you want to put these components into. This is part of that, and I'm happy to go into that. But the bottom line is the capacitive transduction. We're driving using the gate dielectric. We're sensing using transistors, which is efficient and nice, but the drive using capacitors is inefficient. That K squared, that conversion from electrical to mechanical energy is 0.01% or less. And that's a fundamental limit of these dielectrics, that that the energy stored in that capacitor is just not high enough. And so it makes it very, very challenging to close the loop and make an oscillator. So I think there are ways to do that even with these devices, and we are working on the closing the loop even in a vanilla process. But it's also an opportunity for us to look forward at many emerging device opportunities and emerging transducers. One very low-hanging fruit is in terms of emerging transducers in CMOS is piezoelectric and ferroelectric transduction. So ferroelectrics are already, and have been for a couple of decades, integrated into back end of line in CMOS and increasingly into front end of line in CMOS for memory devices, for non-volatile memory. PZT has been around for quite some time as a back end material, and people are looking at HZO, hafnium doped, hafnium zirconate, as a front end for ferroelectric transistors and ferroelectric capacitors. There are also increasing number of foundries that are integrating materials like aluminum nitride into their technology, into their platforms. This is often back end of line addition. So after BEOL, post processing, adding layers for aluminum nitride. We saw that example with Texas Instruments dual Bragg bulk acoustic wave resonator, but TSMC. There are microphone opportunities, piezoelectric microphones, ultrasound transducers, and things like that that are being monolithically integrated on top of CMOS now using these piezoelectric films. There are other opportunities moving forward. They're more 10 years down the line, or may have other barriers to entry, but I'll put them out there as opportunities to excite and sense acoustic vibrations. If you want to get phonons involved in your circuit's phase change and phase transition materials, experience a large volumetric change with their phase transition, magnetostrictive materials. So if you do have magnetic films, anybody working in spin torque oscillators, but also in filters, there are YIG oscillators and others that may leverage this kind of technology, and of course optomechanical devices, which is an entire field of study of its own. So I'm going to focus on ferroelectric here because it really is the next thing, the next big step for scaling MEMS devices to higher frequency, for integrated devices, and so forth. So I mentioned Texas Instruments has a PZT process that it's 130 nanometers. It's been around since 2004 and is commercially available. And it's basically in the back end of line, these PZT capacitors that can store non-volatile memory based on the hysteresis of the ferroelectric elements. But there are opportunities as well with HZO, as I mentioned, and that is now making its way almost into product. And I think with the CHIPS Plus Act, that is one of the big pushes, is to be able to make memory devices in CMOS. All right, so as far as ferroelectrics in MEMS, there's been a lot of advances over the years and demonstrations of leveraging the tunability and the hysteresis, actually not so much the hysteresis, but the tunability of ferroelectric materials, which translates to programmability. In HZO, in scandium doped aluminum nitride, in PZT, and in BST as examples. But we worked with Texas Instruments and leveraging this concept of these unreleased resonators that are just embedded in the stack with no post-processing, no special packaging, and being able to connect directly to the transistor layer. We demonstrated proof of concept, these arrays of ferroelectric capacitors, and we're able to show some nice performance, which I'll talk about momentarily, with this existing commercial technology. Pros and cons to the different materials. PZT is, has a very good electromechanical coupling, but doesn't scale very well to high frequencies due to electrical losses. HZO is kind of that front runner, I think, moving forward for CMOS integration, although people are looking very aggressively at AlScan the scandium doped aluminum nitride, specifically for filter applications and not so much integrated in CMOS. All right, so we basically in TI's process with these ferroelectric capacitors implemented the same concept of arraying these transducers together and forming particular vibrational modes based on the periodicity of these different materials in order to confine acoustic waves vertically so they can't travel to the substrate, the silicon substrate below, and they don't get lost up into the metallization layers above. And so it looks kind of like this top view over here. So this, remember, is 130 nanometer technology, and our proof of concept was not aiming at very high frequency scaling. We just wanted to see, does this work? And so we chose to go with like a 2 micron pitch, which translates to about 700 megahertz frequency. You can see the device is a little bit larger than the FinFET devices with all of those considerations, but this is a top view showing 7 micron wide, 108 microns to get all the arrays for the transducers, and then that adiabatic reflector transition off at the edges to prevent vibrations leaking out sideways. Okay, so I won't go into the dispersion relations very much, only to say that the mode is very clean relative to FinFETs, because we have there are a lot fewer layers and the entire thing is done in back end as opposed to at the transistor layers. So we had a lot more, I guess, ease of simulation of the geometry relative to reality. But you can see alternating compressive and tensile stress layers in the array of these ferroelectric capacitors. Again, this is the back end of line, so the transistors are actually, they can sit down here, and we're using the polysilicon gate to tie these all together to ground in this particular case. And so here's that targeted mode, and then off at the ends you can see the evanescent mode, which tails off, essentially forming this mirror which confines us laterally. So using these devices, we were able to show, again, we've got a ferroelectric material. So depending on it, the biasing on it, depending on where in the on the polarization electric field or PE loop we sit, remember these are hysteretic devices, we can excite either poles or zeros in the resonance. We can tune the frequency a small amount, 1% or so, but that's enough to compensate for, let's say, fabrication variations, for temperature variations as you're using the chip. And so we can get a full and hysteretic programming of this resonant device using the ferroelectric properties. So you can imagine making adaptive filters, you can imagine making tunable frequency sources and various other things. Now, realistically, you know, there are all these benefits to ferroelectrics that we really want to leverage, but in order to be able to implement these now nonlinear hysteretic devices in any real circuit, we need large signal models. And so we actually developed the first full large signal model of ferroelectric transducers, in this case, using the experimental results from our TI FRAM process, but can be translated to any ferroelectric transducers out there. So looking at how the transduction and the resonator behavior performance varies with not only bias, the DC bias, the polarization that's across this capacitor, but also how it varies with power. So depending on the power input, you know, because these are nonlinear transducers, you'll exhibit nonlinear behavior in your output. We characterize that under different biasing conditions and so forth in order to see, well, if I want to maximize that nonlinearity, if I want to minimize that nonlinearity. And you can imagine, for example, in a filter, you could use it to trigger a particular change in your spectral mask if your antenna input power goes above some threshold. So you could automatically sense your the spectrum around you and dynamically notch out interferers, for example. So there are opportunities in that space, but also opportunities in, again, in sensor computing, where you're performing these functions, storing information in the hysteretic properties built into the transduction to how you're modifying the device itself. So a lot of exciting opportunities in that space. So to wrap things up, kind of looking at the impact of these MEMS devices, you know, if we can get, for example, ferroelectrics in integrated circuits combined with high frequency MEMS resonators, there are fantastic opportunities in next generation wireless communication, which means, you know, autonomous frequency agile radio front ends with spectral sensing kind of built in. In the space of Internet of Things, which may be an outdated term now, some people are moving on to just, you know, assuming we just need sensors and everything. But I'm going to keep using this term for a little bit. But obviously, if we can get clocks on chip, for example, if you could get monolithic sensors that are built in and stealthy, by the way, you know, looking at the chip, you don't necessarily know what it is, and the fact that there is a sensor built into it, there may be benefits there. It translates to low swapC, but with the opportunity to embed physical and chemical, environmental sensors, and so forth. And all of that also means that we develop a resiliency against supply chain issues in semiconductors. Because if I can make all of these different functional devices, sensors, clocks, filters in standard IC technology, and we're investing so much in standard IC technology manufacturing here, even if it's in 22 and 28 nanometer, and, you know, obviously 3 and 2 nanometer technology might have other limitations and may not be the appropriate one for these devices, might be, then we can, you know, achieve much more in micro manufacturing here in the States, rather than having to go offshore for those aspects. So there are benefits to being able to achieve functionality with redundant, like with the same technology platform that's used for microelectronics. That also presents opportunities for hardware security. If we can make basically transducers, ultrasound transducers, which is basically what all of these are, inside the chip. So a couple of benefits. One, well, if I embed the clock inside the chip, I don't have a pin to the clock that can be disrupted, that can be glitched, that would compromise my entire chip. Additionally, if I have transducers built into my chip, I can interrogate the geometry, the routing, the placement of transistors, the integrity of interconnects and packaging at any step in the process. I could do it partway through the metallization layers, if I can have kind of short loop access at depending on how you define any probe pads for testing. But I could also interrogate in the field post-packaging to see if anything has been modified or tampered with on the chip. There are obviously also opportunities in biomedical space. When I have these transducers that are built in, I can make arrays of them, phased arrays, and tunable beamforming. Okay, 2 seconds to say it's not all about silicon. And now with heterogeneous integration and looking at the best material for the job, there are plenty of opportunities to work in other competing or complementary semiconductor platforms. Gallium nitride is one we've worked in for a very long time and demonstrated monolithic oscillators, high Q resonators and filters, and lots of opportunity in that space, especially now if we're thinking about about that heterogeneous integration, 3D or system on chip, to leverage MEMS in these multiple technologies. Lithium niobate is also emerging as a platform for active devices. Sandia National Labs has done some fantastic work in that space with InGas on lithium niobate. And we've worked with them to demonstrate some really nice performance devices with terminal gain, particularly for radio communications. I'm happy to elaborate on that more in detail if anybody's interested. But really kind of looking at the landscape ahead, it's an exciting time to be in semiconductors, in microelectronics, and in MEMS, and thinking about that, leveraging existing and emerging technologies, technology platforms to build new functionality. And I'm particularly excited from the timing application on integrated clocks, right, at the front end. Lots of opportunities in that space, and hopefully get a chance to work with some of you to figure out, how to do that best for your applications. Just a quick ad for any of you who may not be plugged into these communities. So the ultrasonic ferroelectrics and frequency control community may be of great interest to you. Frequency control symposium coming up in Toyama, Japan, we work on MEMS-based resonators, but the community includes, all the way up to ion clocks. So depending on your needs for stability, the full spectrum is there at this particular society and this particular conference as well. And then I am chairing the MEMS 24 conference in Austin, Texas in January. So there will be certainly more timing and filters there, but a whole lot more. So please check it out, if you're interested in looking more at these communities. Thanks everyone for your time.
Wonderful. Thank you very much, Dana. Let's open the floor for questions. Any questions? Maybe again, I start with a question. How is this, let's say, do you put in the scope also, let's say, surface plasmons?
Do we put in the, say again?
Like we have like those elements, let's say you had various transducers and so on, like different phenomena basically. So would surface plasmon also fit there, or?
Okay, so people, depending on the frequency range of interest, that's certainly possible, right? That's there's a lot of metamaterial work going on in that space, and you can certainly design the CMOS backend in order to resonate in particular plasmonic modes. We're not doing that at this point. We'd like to stay a kind of white spectrum in infrared absorption, and try and keep things as cool as possible. Although there are opportunities, for infrared sensors and various other sensor applications to look at that. Absolutely.
No, the main reason is because I think you saw this paper was published in Nature by fellow Mohammed Niku, which was about a terahertz electronics basic's, and I think it was based on, from what I understood, it was like surface plasmon. So I want to see where is the the common and where it basically diverges from.
I see. Yeah. So in all of these cases, I guess whether you're looking at plasmonics, whether you're looking at photonics or phononics, we're basically all defining these resonance eigenmodes in these periodic structures. We're all just using the wave equation more or less, but slightly different polarizations and various things involved. But yeah, obviously, so the math can be quite similar. Of course, the physics, the loss mechanisms, and the radiative properties can be substantially different. Yeah. So in acoustic waves, we have the, I guess, misfortune of dealing with a few more polarizations than
Yes.
the others do. So the structures and the scattering of the modes can become, you have to really design for it.
Yeah.
But there are, yeah, the periodicity and the number of layers that are afforded by CMOS technology relative to what we could do in an academic foundry, for example, or even in a kind of startup environment, mean that we can clean those up quite well, clean those modes up very well.
Yes. Any more questions? Hearing none, another question. So the device that you mentioned about the was a ferromagnetic, I think, right? Like a MEMS thing. Would that
The ferroelectric.
ferroelectric? Yes. So and that's basically based on hysteresis. Is that something, I don't know, I was not aware of this, like let's say for the non-volatile memories, like all I knew was like a floating gate. Is that something
Ah,
that is coming? It's like, because this can
oh
solve a lot
yeah,
of problems. Let's say, is that in production? Is that looked at?
yes.
Yeah, so
So all foundries are looking at ferroelectric memory now. There was a period of time where people were looking at negative capacitance FETs,
huh.
and trying to engineer the band, basically the energy profile of that capacitor using ferroelectrics in order to make really efficient circuits. That's not working out so much, but there's been a phenomenal work in that space, but in terms of practical implementation, that's not working out. But all of the materials development that went into the thin ferroelectric films has made it kind of the front runner for non-volatile memory. And so now there are two options, right? So back end of line ferroelectric capacitors, and then front end of line integrating that ferroelectric at the transistor gate. And so FE FETs are the front runners for, for memory devices moving forward. So foundries all have capabilities in this space. We know, Global Foundries has been working on this for a long time, and while the films, I think, are deposited out of the country, they go back to in-country fabrication. So these are already available. They're not being commercially deployed yet in multi-project wafers for us lowly researchers to use. Not yet.
Interesting.
Maybe I'm hoping a couple of years.
And then do you see also memristive properties in these materials?
Not in these, no. So these are not memristors with kind of that ion channel charge sloshing. No, these are ideally very, low leakage, just hysteretic polarization built into each one of these elements, into these ferroelectric FETs. Yeah.
I'm still like waiting to see when is basically when are we going to use like this memristive properties, even like in theoretic to, like, let's say, I mean the breakthrough in 2008, and then with like titanium oxide, like and then I see a lot of these things are, everything is around it. It's like the elephant in the room, it feels.
Yeah, so memristors, yeah, I guess they're not, I can't say specifically why they fell out of favor as the front runner for memory devices, but I guess in terms of speed, reliability, and low leakage, the HZO and silicon doped hafnia as well are kind of, they're being implemented at full circuit scale, but not yet widely available.
Yes,
So,
yes.
yeah.
Okay, great. See, people are leaving because we went above time. Any more questions here before we call? Okay, hearing none. Again,
And I'm
Dana,
happy. Yeah, I'm happy to answer anything offline if anybody has any questions later on. Thank you. Thank you so much for the
wonderful.
invitation.
Wonderful. Thank you very much, Dana. Also, okay, I'll just stop the recording.